Arc blast is a dangerous electrical explosion that happens when high-voltage electricity jumps across a gap, creating a powerful arc of fire and molten metal. Even though both the 12.5 kV and 480 V sides may have the same amperage, like 200 amps, the arc blast in the 480 V side is much higher, and this is due to a few reasons. Firstly, lower impedance. Impedance is the resistance to current flow. The impedance at the 480 V system is much lower compared to the 12.5 kV system. Lower impedance allows current to flow more easily, resulting in a more powerful arc. Secondly, higher energy density. Voltage is the pressure of electricity, and it determines the amount of electrical energy stored. While the amperage is the same on both sides, the voltage on the 12.5 kV side is much higher. This means there is more electrical energy stored in a 12.5 kV arc, but due to the higher impedance, it is released more slowly. Thirdly, smaller gap. The gap between conductors is smaller on the 480 V side compared to the 12.5 kV side, as the 480 V equipment is typically more compact. A smaller gap makes it easier for electricity to jump across, resulting in a more severe arc blast. Think of it like two water pipes, one with high pressure, like the 12.5 kV, and a small opening, and the other with low pressure, like 480 V, and a large opening. The high pressure water will shoot out more forcibly through the small opening, like the 12.5 kV arc, but the low pressure water will flow more freely through the large opening, like the 480 V arc, resulting in a larger and more powerful spray, which is like the arc blast. To elaborate further on impedance, consider it as the total opposition a circuit presents to alternating current. It encompasses both resistance and reactance. Resistance is the opposition to current flow in a direct current circuit, while reactance is the opposition to current flow due to capacitance and inductance in an alternating current circuit. In the context of arc flash, lower impedance translates to a higher fault current. A higher fault current means that more current is available to sustain the arc, leading to a more intense and destructive arc flash event. The 480 V system generally has a lower impedance path to ground compared to the 12.5 kV system. This is primarily due to shorter conductor lengths and larger conductor sizes typically used in 480 V systems. Shorter conductors have less resistance and inductance, while larger conductors have lower resistance. The grounding system design also plays a crucial role. A solidly grounded 480 V system provides a low impedance path for fault current to flow back to the source, whereas a high resistance grounded 12.5 kV system intentionally limits the fault current. Now consider energy density. While the 12.5 kV side has a higher voltage and thus stores more electrical energy, the energy release rate is low due to the higher impedance. The 480 V side, despite having low voltage, has a lower impedance, allowing for a faster release of energy. This rapid energy release is what contributes to the more intense arc flash. The energy released during an arc flash is proportional to the square of the current and the duration of the arc. Since the 480 V system can deliver a higher fault current due to its lower impedance, the energy released during an arc flash can be significantly higher, even if the voltage is lower. Furthermore, the smaller gap between conductors in 480 V equipment contributes to a higher probability of an arc flash occurring. The dielectric strength of air is approximately 3 kV per millimeter. This means that a voltage difference of 3 kV can cause the spark to jump across a 1 mm gap in air. In 480 V equipment, the spacing between conductors is often smaller than in 12.5 kV equipment, increasing the likelihood of an arc flash. The compact design of 480 V equipment also means that there is less space for the arc to dissipate, leading to a more concentrated and intense arc flash event. To further illustrate the concept, consider a simple circuit with a voltage source and a resistor. The current flowing through the circuit is determined by Ohm's law, which states that current is equal to voltage divided by resistance. If the resistance is low, the current will be high, and vice versa. In the case of an arc flash, the arc itself acts as a resistor. The lower the impedance of the system, the lower the resistance of the arc, and the higher the current that will flow through the arc. This high current is what generates the intense heat and pressure associated with an arc flash. In summary, the higher arc flash hazard on the 480 volts side of a transformer is primarily due to the low impedance of the 480 volt system, which allows for a higher fault current and the faster release of energy. The smaller gap between conductors in 480 volts equipment also increases the probability of an arc flash occurring. Understanding these factors is crucial for implementing effective arc flash protection measures, such as using personal protective equipment, implementing engineering controls, and following safe work practices. Now let's talk about practical implications. When designing electrical systems, engineers must consider the potential for arc flash and implement measures to mitigate the risk. This includes selecting appropriate overcurrent protection devices such as fuses and circuit breakers to quickly clear faults and limit the duration of an arc flash. It also involves designing systems with higher impedance to reduce the available fault current. This can be achieved by using longer conductor lengths, smaller conductor sizes, or by adding impedance devices, such as reactors, to the circuit. In addition to engineering controls, personal protective equipment, or PPE, is essential for protecting workers from arc flash hazards. PPE includes items such as arc-rated clothing, face shields, and gloves. The level of PPE required depends on the potential arc flash hazard, which is determined by performing an arc flash hazard analysis. An arc flash hazard analysis is a study that calculates the potential incident energy and arc flash boundary for various points in an electrical system. The incident energy is the amount of energy that a worker would be exposed to during an arc flash event. The arc flash boundary is the distance from the arc flash source at which a worker would be exposed to a potentially fatal level of energy. The results of the arc flash hazard analysis are used to select the appropriate PPE and to develop safe work practices. Safe work practices include energizing equipment before working on it, using insulated tools, and maintaining a safe working distance from energized equipment. It is also important to provide workers with adequate training on arc flash hazards and safe work practices. Training should cover topics such as the causes of arc flash, the effects of arc flash, and the proper use of PPE. Regular refresher training should be provided to ensure that workers are up to date on the latest safety procedures. Arc flash is a serious hazard that can result in severe injuries or even death. By understanding the factors that contribute to arc flash and implementing effective protection measures, we can significantly reduce the risk of arc flash incidents and protect workers from harm. In conclusion, even though the amperage may be the same on both the 12.5 kV and 480 volt sides of a transformer, the arc blast is typically higher on the 480 volt side due to lower impedance, higher energy density at the point of arc initiation, and smaller gaps between conductors. These factors combine to create a more intense and dangerous arc flash event. Remember that safety is paramount when working with electrical systems, and it is crucial to take all necessary precautions to protect yourself and others from arc flash hazards. And also do not forget that local codes and regulations may differ. Firstly, it is vital to consult with qualified electrical engineers and safety professionals to ensure that electrical systems are designed and maintained in accordance with applicable standards and regulations. Secondly, regular inspections and maintenance should be performed to identify and correct potential hazards before they lead to an arc flash incident. Thirdly, a comprehensive safety program should be implemented to provide workers with the knowledge and tools they need to work safely around electricity. By taking these steps, we can create a safer working environment for everyone. Therefore, understanding the principles behind arc flash and implementing appropriate safety measures is essential for protecting personnel and equipment from the devastating consequences of this electrical phenomenon. Finally, remember that this explanation is simplified and does not cover all aspects of arc flash. For a more in-depth understanding, it is recommended to consult with qualified electrical engineers and safety professionals. The information provided here is for educational purposes only and should not be considered a substitute for professional advice. Always follow safe work practices and consult with qualified professionals before working with electrical systems. Electrical safety is everyone's responsibility.